I'm Ortwin Gerhard. It's not on the view graph. I work in MPE in Garching, and I'm going to tell you something about the dynamics of the Milky Way. And here's the outline. I've divided it into 4 parts. And today I like to give you a short introduction, where I also thought it was kind of important to include some information about the formation of these galaxies. So one has the cosmological background for dynamics, because dynamics is to some degree dependent also on what you start with, and that comes from earlier on. And then I like to tell you something about the fundamentals of stellar dynamics, distribution functions, and other things, and see how far I get. So a lot of this you can read in this excellent textbook, or its new edition, 2008. And so I don't think it's neither possible in 5 lectures to cover all that's in here, nor is it very useful. Probably take about a 6-week course. And so I thought what I do is I will cover some selected areas from dynamics and try and relate them to what we see in the Milky Way also. And then for some of the more technical things, I would recommend you to go to this book and study it in quiet. So first, the context. So I like to tell you very briefly about the Milky Way as a typical disk galaxy. And also, we haven't heard about Gaia yet, but we'll show you 1 or 2 plots illustrating Gaia's impact on galactic dynamics. Then I like to tell you a little bit about galaxy formation, how we think we understand it at the moment. And then a very brief summary of some of the slow galaxy formation processes that happen in a disk galaxy like our own. Okay, so here's 2 typical galaxies. This one nearly face on, this one nearly edge on. They may not be so different from our Milky Way. This galaxy here has what's called a boxy bulge or box peanut type bulge, which is believed to be the inner 3-dimensional part of a galactic bar. And otherwise, it's a very nice thin disk galaxy, maybe quite similar to ours. This galaxy here is also showing a central barred structure and a sequence of rather tightly wound and not particularly strong spiral arms, which tend to be the points where you find the young stars, the H2 regions, and the star formation based on the cold gas that's still available for such star formation. So the Milky Way consists of about 10 to the 11 stars, roughly. Total mass in stars, about 5 10 to the 10 solar masses. Most of these are in the disk, perhaps 15% in the central bulge, the boxy bulge. And that has a radius of roughly a kiloparsec or so, maybe a little more. Then the double thickness of the disk, about 500 parsecs. So you can see compared to the solar radius from the galactic center, about 8 kiloparsecs, that's a rather small number. And so the sun just happens to be at some sort of fairly far out place in the disk, and unfortunately right in the midplane, in the middle of the layer of gas and dust that obscures our view. There's still about a few 10 to the 9 solar masses of cold gas left in atomic and molecular form in a thin disk. This molecular gas tends to be concentrated within the solar radius, even further in, whereas H1, the atomic hydrogen, can be seen to very large distances. I say 10 to the 9, few 10 to the 9 solar masses left because, of course, originally galaxies started out as almost all gas, and so this stage today is not necessarily typical for the stage of our Milky Way when a lot of the old stars were made, which perhaps corresponds to redshift of 2 or so. So the two gas phases, together with also ionized gas and dust and some cosmic rays, they form what's called the interstellar medium, which tends to be organized in a rather non-uniform way. It's sometimes described as clouds, molecular clouds, H1 clouds. Probably this is a rather continuous set of structures in what's believed to be a turbulent interstellar medium, with a lot of small high-density regions organized into larger and larger massive objects that now we call clouds. And stars form in the cores of those densest parts of these clumps, and then they eject energy and also chemical elements, as we heard just now, back into the interstellar medium, which are then there to be reprocessed into new stars. So the dynamics is dominated in some ways by the dark matter halo that, according to the recent estimates, is somewhat in excess of 10 to the 12 solar masses and a virial radius of something like 200 kiloparsecs or so. That's one of the big problems, of course, in astronomy, as you know, that we haven't really found out yet what this dark matter is. So people are looking for elementary particles that could make it up. And what we know is that it interacts with the rest of the matter in the Milky Way only through gravity. And then again, typical, we have a black hole in the center of our Milky Way. It happens to about 4 million solar masses. It's coincident with the radio source Sagittarius A star and rather close to the center of the galactic coordinate system. Now, stars in the Milky Way have a variety of ages, as you also will hear. And the age of the older stars is of order 10 to the 10 years, maybe a little more. The oldest stars will be found in globular clusters, some in the old disk and many in the bulge. Compared to those 10 to the 10 years, the dynamical time is perhaps one way to characterize this is the rotation period of the sun, something like 200, 250 million years. And if you set these two numbers in proportion, then you find that the Milky Way is about 40 dynamical rotations old. That's rather a short number, a small number of rotations. If you compare that with the planetary system on the Earth, which is about a billion times a typical rotation old. And so that means the Milky Way can be a lot further from equilibrium, let's say, than the solar system can be. But still, it's useful to approximate it as something like a steady state that in some sense evolves slowly as various processes contribute either mass or processes that cause the velocities of stars to change, etc. And some of these processes are to do with minor mergers, accretion of gas from the nearby universe, but others are sort of completely internally driven. So I think one sees from this already that the dynamical evolution of a system like the Milky Way is not entirely self-made. It's also due to the external environment. Now, here are two galaxies. I just want to show that very briefly, how things are different at different wavelengths. And for example, here you see the far ultraviolet radiation of some galaxy compared to the near-infrared radiation. The former is mostly dominated by the young stars, which are sort of concentrated in the star-forming regions along the spiral arms. The near-infrared is to a much larger degree due to the older stars, and therefore it shows more homogeneous structures. And when you look at this in different regimes, you also see that the gas phases tend to be concentrated in spiral arms, not entirely, but to some degree. And for example, this galaxy here, in the optical looks rather innocuous, but I believe it's one of the galaxies that if you look at in the infrared, then it has a central bar as well. So why is that important for dynamics? Only because if you, for example, like to look at the distribution of O stars in the galactic disk, you're going to have a different distribution than if you look at the distribution of older stars. And so one needs to have these things in mind and understand exactly what one's trying to achieve. So this is the same plot, set of plots for the Milky Way. Now from the solar perspective, it's a bit of an old diagram now, but still shows some of the essential features. This is the infrared view of the near-infrared view of the galaxy, a montage from the Kobe-Derby satellite data. You can see here the disk and the central boxy bulge. If you look carefully, you find also that this bulge is not quite symmetric between the two sides. That's the signature of the bar in this image here. At the same time, in the optical image just below, you can see the bulge, but it's very much less clear because of all the intervening dust that you see. That dust is something that disturbs our view at the moment for the next few tens of million years, probably. And so one needs to have some way of dealing with the dust, even also in regard of the Gaia data that's to come. Here you see the far infrared emission, the molecular hydrogen emission, and the atomic hydrogen emission. These are all components that are much more concentrated to the plane, as you can see. And they are characteristic of also young stars. Young stars form in these gas layers, especially the molecular hydrogen. They then, with their energy output, heat the dust grains that you see emitting in these far infrared wavelengths. So that's the multi-wavelengths Milky Way. So now let's come to what Gaia will do. Gaia is a mission to be launched very soon. It will observe about 1 billion stars in the Milky Way. That's just an amazing number. For many of us are used to work with samples of hundreds of stars or thousands of stars, if they're good. But 1 billion stars, just imagine what you're going to do with 1 billion stars. Making a dynamical model for that number of stars. Amazing. Angular resolution like the Hubble Space Telescope. And it'll give us data from 3 simultaneous observing modes. One, it'll do astrometry, measure parallaxes, and also measure proper motions for this sort of large number of stars. Secondly, it has an instrument that can do spectra at some limit resolution, and so one can get radial velocities to not quite the same depth as the proper motions. So it's only 150 million stars, which is still an amazing number. And then it'll also be possible from these low-resolution spectra to get stellar parameters for at least the brighter of these stars. And so that means we'll also get some information on populations from the data that's going to come. Now, this observations will be carried out for about 5 years after the launch. And then until the final data are provided, it will take about another 3 years for constructing the global astrometric solution. But there will be intermediate releases of data, I believe, starting something like 2 or so years after the launch, various parts of the data. So this is a plot that shows you what the volume of the Milky Way will be that Gaia will cover. This is based on the picture that we saw earlier from Jerry's lecture, the sort of current artist image of the Milky Way, the sun being here, and then the color of this plot, which is constructed with the so-called Gaia universe model, tells you about the source density that you can see in these Gaia observations. And this is the face-on view of the Milky Way, and this is the corresponding plot in Edge-on, where the sun is here. So you can see that pretty much half of the galaxy, or perhaps a third, will be covered very densely, and some of the dense fields will be in the bulge as well because there's just many stars there, and it will reach approximately to the far end of the bulge, however, at some lower density of stars. But thinking that this total is a billion stars, there'll still be a lot of stars even here, even though as you go away, the accuracy goes down with some of the measurements that can be made. And so that's shown on this plot here. This is the transverse velocity accuracy that Gaia is expected to reach. And here on this axis is this velocity error, and then this axis here is the distance to the star. And then these various curves are for different stellar types. And you go here from the K-dwarfs up the main sequence, and then reaching A stars, and this green curve here, and then these are then curves describing some of the red giants. And so for the typical accuracy we would like for galactic dynamics, which is of order 10 kilometers per second, that's reasonably accurate already, given circular velocity is about 220 or so. We could expect such accurate data, you can see, depending on the stellar type, for stars of distances somewhere between 3 and 10 kiloparsecs on the scale. And some of the very bright stars, of course, this will go much further. And I understand that one's also expecting to be able to measure transfer velocity of some of the brightest stars in M31. So it's a very rich data set, and it'll give us very accurate data for many of the phase-space coordinates. And this is my next plot, which comes from an article that Jerry Gilmore wrote on. Basically, he was making the point that with the position data that we've basically had for a long time on the sky, except now we're going to have it in some enormous precision, we will also get parallaxes and therefore distances for many stars in this amazing number of stars within the volume indicated on the previous plot. Then with the distances and the proper motions, you can get transverse velocities, as I just showed you. So now by that time we have a 5-dimensional phase space covered. And then given the spectra, we can have radial velocities, and that in principle makes this a 6-dimensional phase space. So we can actually place a star with all this information at some place in space and some place in velocity, which means that if we know the potential of the Milky Way, suppose, then we can actually, from that data, see what the star's orbit is. Or vice versa, we can hopefully try and use all this information in order to infer the galactic potential from these data. And this diagram was made, of course, because there's some need for follow-up ground-based observations, basically spectra, to determine further radial velocities and also detailed abundances for these stars. And this is the purpose of, in this case, the Gaia ESO survey. Okay, so that much for the Milky Way and Gaia. Now I'd like to switch a little to the topic of how galaxies like the Milky Way may have formed. And as I said, the reason for discussing this is because, in some sense, the dynamics of what the galaxy that we see now is somewhat influenced by ideas that come and results that come from this galaxy formation process. So that's a subject that's been evolving very rapidly in the last years. And we now believe that we have a working model of how all structure forms in the universe, where we essentially know the initial conditions. These initial conditions are imprinted in the microwave background, so we know the fluctuation spectrum at large scales. We can also use a variety of lensing observations to measure it on smaller scales. And together with various observations and models of the large-scale structure, it appears that the so-called lambda CDM cold dark matter model gives a very good description of many of the aspects of the structures that we see in the universe. Perhaps with one exception of the smallest scales in galaxies. And one of the characteristic features of that model is that the growth of galaxies is dominated by the dark matter. And in the dark matter, it happens hierarchically. It means that the smallest structures form first, and then they merge, and then they merge again, and then they come together to build even larger structures as time progresses. Now, another aspect of this hierarchical galaxy formation model, is that galaxies always interact with their surroundings. And that's also relevant today. That means they're not independent of their surroundings, as a long time ago it was once thought. They're not distinct systems of gas and stars that just evolve on their own, but they constantly interact with their surroundings by a variety of ways. For example, they might interact gravitationally, just with the surrounding dark matter halo, but some galaxies also clearly interact with the tidal fields of larger structures in which they move. For example, galaxies in groups and galaxies in clusters feel the tidal fields of both other galaxies in the cluster, but also the mean dark matter distribution, which by itself may not be smooth. Now, exactly how smooth or unsmooth the Milky Way halo is not so well known observationally, although I'll show you how it's believed to be theoretically. But that's one way in which the present galaxy could still be influenced by its environment, is by the lumpiness in the dark matter halo that interacts with the stars. Now, there's also the aspect that galaxies generally are affected by mergers. Now, mergers could be with large systems. That is rather rare. And however, it's predicted from recent data, I'll show you in the last day, that our Milky Way will have a major merger in the future with Andromeda, because Andromeda is on a direct collision orbit with us. As far as we can tell, it's on a direct orbit towards us. So it'll be only a matter of waiting for a while until, presumably, then our Milky Way gets transformed into a typical elliptical galaxies, let's say, of the kind of galaxy like Centaurus A. Now that's, however, rare. What's much more frequent is minor mergers, and minor mergers can be with galaxies of the sizes like the Magellanic Clouds, which seem to have just entered the halo of the Milky Way, but also with objects like the Sagittarius dwarf galaxy, which already has been interacting with the Milky Way for a couple of orbits, and as I'll show you, has a long tail of stars around the sky, which one can observe and use for a variety of things. And then there are objects that are even smaller, which would be the dwarf toroidal galaxies, or the so-called ultrafaints, which some of which are probably currently being tidally affected by the Milky Way halo, and that's sort of one way of interaction. And then there's the issue that with such interactions you can have accretion of stars, but you can also have accretion of gas in some even more diffuse way, and accretion of dark matter that's predicted to happen even now, although the accretion rates go down quite a lot as you go forward in time in this evolution. So that nothing is significant now as they would have been at redshift 1 or 2. Now, these processes, both the mergers and the accretion, of course, cause a variety of things. They, for one thing, can replenish the gas in the disk. They can, just by the gravitational effects, they can cause extra star formation, and they can also cause structural evolution. For example, they could heat the stars in the galactic disk. Now, I wanted to show you this this movie here, let's hope it works. No. Okay. There we go. Which is from Volker Springel and shows one of the Aquarius halos. Aquarius is a set of simulation that was done by Springel and colleagues at the MPA and together with other groups of cosmologists in order to try and understand how the evolution of the dark matter halo of the Milky Way might have gone. And it's quite instructive to look at because it tells you really that in this hierarchical clustering picture, there's always something going on. And you can see it a little later now, a redshift of 12 here, when you look at the sort of central object that's going to be the halo of our galaxy, and you look at stars, at little lumps of dark matter that go through, how these lumps are going to be deflected on the one hand, tidally affected on the other, and thereby building up the mass of the host halo. Now, what's going by here rapidly is sort of in the foreground because this is made from a perspective rotating around the halo. So look at the objects that go through right here. For example, did you see this one? It suddenly has this amazing tidal halo around it after just going through just once. And this is how you can see how slowly from all the lumps that are accreting, this more or less smooth halo is going to be built up. You can also see that as the simulation here goes forward in time, how the scale bar increases. So we're looking at now a typical scale of a few hundred kiloparsecs in this plot. So here was another object affected by the tides. Did you see? This one as well. Always when you go through the high density regions, there's some tidal shock occurring, and some of the dark matter particles get unbound.
This is just dark matter.
That's just dark matter, yeah.
The different colors are
I must say I don't know what the different colors are. Okay, so now we're nearly present day. You can also see, perhaps this is what I illustrating what I said earlier, is that at the end, the number of objects that are actually falling through is sort of going down with time. No, so activity decreases as you go forward. So I wanted to next show you something about dissipative collapse. That's played some role in the history of galactic formation, and also because it illustrates a few points on how some of the observables might be related. So this goes back to a very important paper by Egan, Linden, Bell, and Sandage many years ago, who pioneered the idea of a rapid collapse formation. At that time, they were looking at isolated galaxies, and they were thinking about the question how the collapse would happen in the presence of angular momentum. And the idea that they wanted to explain at what was at that time believed to be the eccentricity distribution of stars, which seemed to go from low eccentricities for the most metal-poor stars to high eccentricities in the more metal-rich stars. Now, those data have changed in the meantime, but also we've learned that galaxies are not isolated. And so this model here, which I was involved in some years ago, is something like a modern version of the Egan, Linden, Bell, and Sandage picture, in the sense that it uses an accretion history that comes from cosmological simulations. So this was made in order to understand whether it was possible to explain something like this galaxy simply by allowing for this dissipative collapse in the presence of angular momentum and an accretion rate. And if it was, then what would that predict for where stars of different abundance ratios would end up living? So one of the things that turns out here, but also in many other models, is that the galaxy forms from inside out. Now the reason for that is the angular momentum and also the time it takes to collapse. So the material that's further out in the region that's going to collapse to the galaxy generally has more angular momentum and it takes longer to collapse. And so that part of the disk that it collapses to will form later. So the disk grows from the inside out. Another thing that has also turned out quite characteristic is that the star formation rate in the average that you find in these models always follows the mass infall rate rather closely. And that's true for the most modern simulations as well. So that tells you one thing, that clearly the history of the galaxy is very tightly connected with the cosmological formation process. Now it also turns out that then you have essentially two populations built up by this. One is a population that forms in this very rapid phase in the beginning and tends to have a lot of supernovae and therefore enrich the gas with oxygen elements like Francesca was telling us. And then there's this sort of more long period where then the gas infall rate and also the star formation rate go down with time, and where then it's more like a normal chemical evolution, building up disk stars. And these are two populations in principle that's possible to distinguish. Now I wanted to illustrate, this is the inside-out growth, just as an example here. Here is redshift 1, and there's 0.5, and there's 0. You can see very clearly how in this model the sequence goes from a small to a large disk. Also, you can see how the material settles from something that's a bit thick and turbulent at the beginning to a rather thin system. Now, this is now something that people in high redshift observations find quite regularly, that the disks at that time, in redshift 2 or so, are quite turbulent and then presumably thick. And then the thing that we wanted to understand based on this is the reason I want to show this, is because then you have various relations between where stars in the end are found in these galaxies and what their enrichment history was. And so, for example, here is a couple of plots that have been made for stars of different iron to hydrogen abundance according to the prescriptions used in this model. I come to that in a moment. And you can see that, for example, the most mineral-rich stars end up in the center because they're made at the very end from inflows triggered by the bar. But on the other hand, if you look at any given metallicity, you can see that there's a relatively long history of when these stars were formed. And there's also quite a variety of different alpha to iron ratios. That's depending on the time scales with which the stars were formed compared to the gas infall, etc. Now, I wanted to not say really much about the way star formation and so on is modeled in these simulations. This is something that Jerry advised you very strongly against, to make simulation of that kind, because there's a lot of uncertainties here. For example, you need to put in some prescriptions when do you form stars from the gas. You need to put in some prescriptions on if you form stars, how does that react back on the star formation process, the so-called feedback problem, which people have been working on a lot in the last few years. All of these issues are highly uncertain. So you should not view such a simulation, or any of the ones to come, as something that is now true. It's an illustration of how things might happen. And then from that illustration, we could enlarge our mind and understand how certain things might go and what, therefore, we could look for in the data. but not view it as correct. And that's also true for some of the more modern simulation, because people are still struggling with the same issues. They're still struggling with star formation and the feedback. And I think that they will for a while. This is one from, okay, let's see. I can get that to work. Okay. Okay, so this is a simulation from Fabio Governato, who's been one of the people who have recently been able to make realistic disk galaxies in a cosmological setting. And you can see here how the gas comes together and then makes stars. There's going to be blue and red colors. In this case, is sort of young and old stars, and then the grayscale is the gas coming in. You can see how this system starts developing a rotating disk, which, however, can be disturbed quite a lot. Still, it'll be a rotating disk. In a moment, I think you can see how it flips over, or has it already done, just because it gets a big lump of angular momentum from some infalling material. You can also see from the gas how the material comes in parcels. It's not a smooth accretion process. It's one that can be down and up and etc. You can also see at the end now we've got some kind of bar formed in here. So it all looks reasonably realistic. And so the issue is perhaps not whether, so the question, perhaps say it this way, the question these people like to answer when they do a simulation like this is two. First, is it possible to achieve a realistic disk galaxy forming in a situation like hierarchical clustering? And it turns out it depends on several things. One thing is it's very important to have lots of particles, lots of grid cells, a lot of computer resources. But then it depends also very strongly on choosing what's called somewhat quiescent initial conditions. So you don't want to have a halo that merges with the halo of its own mass at a redshift of 1. And it also depends quite a lot on exactly how you treat the feedback in these simulations. In other words, how the star formation impacts on the gas that's making the stars. And so, given all these uncertainties, the questions is really what would we have to assume in order to make it work, and then if it's possible, so that what can we see from these simulations that perhaps can teach us something about what we should look for in the data. So I think this is how one should view these simulations, even though they have a clear lot of uncertainties. So this is one of these simulations. Now in a bit more detail, it's called the so-called ERIS simulation. It's been made by colleagues from Zurich and Santa Cruz. And you can see here a sequence of plots also from one of these, from this ERIS halo and ERIS galaxy. You can see the object here forming a bar and then being disturbed by some minor mergers that destroy the bar, having the bar reformed, then weaken it at the end. And the end, there's this what's called pseudo-bulge. We'll come to this in one of the next lectures. A pseudo-bulge is, I think, a bit of an unfortunate word, but it's used to describe bulges that are made from disks, fundamentally. And you can see that despite all the details, that in the end you end up with a realistic disk galaxy at some level, and you can make stars in these systems that look a bit like real galaxies do as well. And I wanted to illustrate two things on this. One is, if you look at this diagram here, you can see how the disk scale length in such a simulation increases as you go forward in time, from a very small value at a redshift of 4 here to something like a Milky Way type value at redshift 0. So this is again the inside-out growth. It means that higher angular momentum material takes longer to settle into the disk. You have bulge to disk, bulge to total ratios that are somewhat realistic. And for these disk-made bulges, also the photometric structure, which is measured by the surface index in this case, is around low values, which is also more or less like observed. And some of it, of course, depends exactly on the feedback model, etc. But that's clear in some way. And perhaps the last thing I want to show you about this simulation is this plot here. Again, only to illustrate what's possible, rather than claiming that this is necessarily or necessarily correct. But because of the inside-out formation process that's happening in the simulation, what's also happening is that there's a clear separation between the age distributions of what's called the bulge here and the disk on this side. And bulge here defined to be basically stars on non-circular orbits in the center, and disk everything else. And you can see that when you look at these two plots here, that most of the bulge stars were actually formed quite a long time ago, and most of the disk stars, even though a fair number was formed a long time ago, there's still a lot of disk stars being made today. And so the mean age, as you go from the center here to the outside, shows a very clear decrease. So the youngest parts of the disk are furthest out. In particular, the central bulge region seems to be quite old, which is one thing that's also observed in the Milky Way. So this is not a model for the Milky Way in detail, but it illustrates this particular point. So the last thing on this simulation I wanted to show you is this is now a comparison of several of these recent models done by Obreja and others. And they've been using simulations from various people, different codes and different feedback recipes and so on. And what this plot shows is, again, that the star formation rate in almost all aspects follows the mass accretion rate very closely, meaning that the evolution of these disks is, to some degree at least, dominated by the interaction with the environment, the accretion of mass from the nearby surroundings. And in all cases, you have this rather steep, not all cases, there's some that are a bit different, but generally you have this steep increase in the beginning, and then some sort of more gradual tapering out towards the present day. Okay, so much about galaxy formation. Now I wanted to just very briefly tell you in words something about galaxy evolution through secular processes. We'll come to that a little more. And I've just listed a number of those here. There's a continuing accretion of gas, also of dark matter, of little satellite galaxies, and therefore sometimes of stars. There's the growth of the disk in mass and size, which by now is a rather slow process. There's the halo streams that we'll talk about a little later. There's possibly effects of some of these satellites going into the galaxy, scattering disk stars, and then perhaps creating a hot, thick disk component. This is one of the models that's been discussed. There's stability and instability processes in the disk, both to spar and spiral modes, which may grow. The bar mode may evolve into a nonlinear bar structure that by itself can become unstable again and make a boxy peanut bulge, as we see in our Milky Way. And then there's also heating processes by gravitation perturbations, radial migration, and then inward motion of gas mediated by gas and spirals, and subsequent star formation in the center. So all of this may go on as our galaxy ages and becomes more mature in the sense of having more stars and less gas with time. Now, I won't illustrate these now. I want to just show you this one plot showing the formation of a barred structure in the disk and the simultaneous thickening of this bar after here you can see this slightly asymmetric phase in the evolution, indicating that here we're talking about a so-called buckling instability. Okay, so much about galaxy formation. So now, what are the tools of galactic dynamics? So we're going to use stellar dynamics. This is basically application of Newtonian mechanics to systems of stars or other point masses. You can do this in two ways. You can try and make some progress with analytical models and perturbation theory. Increasingly, this becomes difficult because what can be done has been done. And as Jerry said, for many of the nonlinear processes, you need to do numerical calculations. Still, it's I think useful to go through some of this, and it draws from various fields of mechanics and physics. Of course, the entire field of how you treat the gas in this system is completely different. Then you need to think about hydrodynamics, the application to fluid dynamics, to an interstellar medium, which is rather complicated by itself. And that is only possible, I think, fundamentally with numerical simulations. Now, I like to also distinguish between different time scales. There are fast processes, like the collapse, that happens on a dynamical time scale. And then there are slow processes, and maybe even quasi-equilibria, that happen on time scales that are much longer than dynamical time. And sometimes it's useful to consider true equilibria also, simply because it's easier to deal with them. But probably they would be rarely present in the real universe. As you saw, there's also always something falling in. There's always something disturbing your equilibrium. Okay, so much about the introduction. Now I want to sort of come to the fundamentals of stellar dynamics. Basic collisionless stellar dynamics, a bit on the Viral theorem, phase-space distribution function, Boltzmann equation. Then we're going to talk about moments of the distribution function, the Jeans equations, what it means to have stellar dynamical pressure. And then I'll talk about the Viral theorem a bit, and also how this relates with the flattening of stellar systems. And then, well, not all of this will be possible today, but after this, there'll be then a second part on the orbits of stars in galaxy potentials. Okay, so let's start with the Viral theorem. So this is a very old result, so I can use a very old slide as well. So we start from the Newtonian equations for a set of point particles here. Each of the point particles has a Keplerian gravitational potential. Now, the part of the view that's not quite so true anymore is today. Now we can solve these equations for probably about a million particles or so by direct numerical solution for star clusters maybe, and we can do it perhaps for 10 to the 9 particles or so in the best simulations for a mean field n-body calculations. Now, these equations, of course, depend on the gravitational potential, and the gravitational potential is the sum of all these particle potentials. And so, in principle, during a calculation like this potential will change with time. And so, therefore, the energies of individual stars will also change with time. But if the system is isolated, then the total energy will be conserved. And likewise, once you reach a certain quasi-steady state, then you can say something about the structure of the system from the Viral theorem. So this is shown here on the bottom of this slide. So what you do is you take the dot product of this equation with R, and then you sum over all the particles, And then after a little rearrangement, you will find this can be written as the second time derivative of this thing here called the moment of inertia minus this term, which is twice the kinetic energy, and that will then equal this on the right, which is the total potential energy of the system. And so if you then suppose that you reach an equilibrium, then this I2 dot term will be 0, and therefore in equilibrium, then I will have a relation between the kinetic energy and the potential energy of the system. And that can actually be generalized to the so-called tensor-viral theorem, as we'll see later. Now, these terms are written again here. This is the virial I, whose second derivatives were had in the previous equations. This is the kinetic energy, and this is the potential energy. And so it's sometimes useful to rewrite these quantities in terms of very simple mean quantities. So, for example, we could write the kinetic energy as, despite all the complications here, as just 1/2 times the total mass times some characteristic velocity squared, which is called the virial velocity. And we could rewrite the potential energy, W, as something of the same dimensions as this here, by defining a so-called virial radius, RV, in this way. So this will be gm squared over twice the virial radius. And then if you put this into this virial equation here, then you will see that the mean v squared, defined in this way, is going to be equal to gm over twice the gravitational radius. And another way of writing this, if you remember that energy is going to be kinetic plus potential energy, that then this mean v squared is going to be minus twice the energy of the total system divided by the mass. And so then also the virial radius can be expressed in terms of energy as m squared over E. And then finally, there's a characteristic dynamical time, which you would write as the virial radius divided by the virial velocity, the factor of 2. And then, as putting in those previous numbers, you can see this goes like the mass of the system to the 5/2 divided by the energy to the 3/2. And another way to express this also is like 1 over the square root of density, essentially. So the virial theorem, very simple equation, lets you estimate certain quantities for a stellar system from others. For example, you might measure a characteristic radius, and you might measure a characteristic velocity. If you can suppose that the system is in equilibrium, then that tells you an approximate mass, and it's given by the combination of these quantities here. Any two of those will determine the third. So I don't want to talk about tubular relaxation because Jerry did already. So I'll just tell you again what the result is. So for a typical galaxy, because the relaxation time depends only on the particle number and the dynamical time, with these sort of numbers here, you get a very long time scale for tubular relaxation. So that means galaxies in the mean are collisionless systems. Now, it's perhaps worth saying that this is not necessarily only dependent on n, because you also have the dynamical time. So if you make your system sufficiently concentrated, then you could make the dynamical time short enough and get the relaxation time also short. But it just so happens that galaxies are too big for their mass, and so therefore they don't suffer from star-star collisions. Dark matter halos are even more collisionless. Here the timescales are truly gigantic. And then the only systems, stellar systems, which have some possible effects of relaxation are the star clusters and the galaxy clusters. In the galaxy clusters, it depends on the details, but you have a typical number, about 1,000 objects, rather long crossing time, but with 1,000 objects, then the relaxation time is not many crossing times, and so it's about equal to the age of the system. And for a globular cluster, if the mass is this, then you can have relaxation important in the evolution of the system. And this may, depending on the parameters, carry over to some of the densest star clusters in the nuclei of galaxies also. But they tend to be generally more massive, and also velocities are larger, and so relaxation times tend to be longer also. Okay, so we can say we neglect collisions, and then it means several things. First of all, we don't care about correlations between stars anymore. So therefore, we can describe the stellar system by a single particle distribution function in the phase space. That's the X and V space. And that distribution function is then evolving as governed by the mean field gravitational potential. We don't need to care about the perturbations to the potential by individual stars anymore. So we can just take the mean field potential. Now this is even more true for dark matter halos, and so also dark matter halos we can describe as collisionless fluids in phase space. Now generally, that doesn't mean we're time independent. Of course we're time dependent. And then the question is, how do we describe that? One way we heard already was by n-body calculations. And then we could also say that because galaxies generally look regular on the sky and have a smooth appearance, they cannot all be in a stage of rapid evolution. So we could suppose that for at least most of them, a nearly steady equilibrium stage has been reached, and the evolution of that equilibrium stage is slow. So it's a reasonable approximation to, for the moment, think of it as a true equilibrium stage and try and investigate the properties of them using such equilibrium models, which are much easier to deal with than fully time-dependent models. So then we'll also ask, how do we describe the equilibrium states? That's Jean's theorem. Come to that next time. And then a much harder question, which of these equilibrium states solutions that we can construct is dynamically stable, and which of them are realized in nature. Okay, I think I have a few minutes more, so let's start with the distribution function. So here is basically this approximation of a mean field potential. So rather than regarding our density field as a set of individual point particles and our potential as a set of individual Keplerian potentials, we can actually describe the system as a continuum, because we know already that the collisional effects between individual stars are small. And of course, in reality, I've vastly exaggerated. These are very small fluctuations on the mean field potential. And then we can define what's called the single particle distribution function F as a distribution of mass, if you like, over the phase space R and V, plotted here as the two axes. And again, we don't need to consider the fact that this particle distribution function consists of individual stars. So there's different ways of defining it. Here I've included the mass into the distribution function. So then you would say this function F as a function of the phase space RV, the mass and time, would be the number of stars with masses in this range here, stellar mass in this range, and live in this phase space element D3V and D3R. If you don't like to consider stars of different masses separately, well, then you just integrate this over the mass, and that's then the total distribution function. But as we saw at the beginning, the distribution of O stars in the galaxy is quite different from the distribution of old stars, K giants, for example, and therefore sometimes it may not be appropriate to do that. So there's two issues here. One is we're talking about a 6-dimensional phase space element. That's rather a large number of dimensions. So even if you have 10 to the 12 stars, that's only 100 per dimension. So you may not be able to measure that distribution function very well. So one way of looking at this is to say you look at certain sort of largish volumes of phase space in which you have enough stars to actually compute the density of them. That's so-called coarse graining approach. Or the perhaps more profitable one where you think of this distribution function as a probability for a star to be in this phase space element. So once you have the distribution function, then you integrate over velocities and mass, and that gives you the density of stars at given radius or position and time. And then from this density distribution, you can work out what the gravitational potential is, either through solving this Poisson's equation or by doing the Poisson integral, which is equivalent to it. And so then you have the mean field potential from all these stars, and then given that potential, you can now evolve that distribution function. So this is the last thing I want to do today. So here we have the Boltzmann equation. Very simple idea. Particles are conserved, so there's no stars being lost anywhere in phase space. Therefore, there must be a continuity equation, and this in this six-dimensional phase space takes this form. Now, you can also write this as in this form here, where essentially what this is telling you is that the total time derivative of the distribution function along the trajectories of the stars is zero. That also means that stars are not lost. Whenever you follow an orbit, well, one star, you follow that orbit and the phase space density is the same. So now you can divide this up. You can say, let's suppose I write my potential here as the smooth potential that arises from looking at all the stars and neglecting two-body relaxation or so completely, plus some difference between that the true potential and the smooth potential, which would be then this right-hand side. See, this is still an exact equation. Now, if we have no two-body collisions and no other perturbing effects, we would simply set this side zero, and then we end up with the collisionless Boltzmann equation in the mean field potential phi s. But it may be at in some applications that there are perturbing forces, perhaps not from other stars, but perhaps from molecular clouds in the disk or from other gravitational fluctuations, and then we may be using this part as well by, for example, assuming these fluctuations are small, and then one can sort of transform into some equations of the Fokker-Planck type, etc. But for the moment, we'll use simply the collisionless Boltzmann equation, which is now this. So it's now in the smooth potential. I've sort of left off the index S from now on. And so we have a system that describes an equation system that describes our stars, which is basically two equations only, the collisionless Boltzmann equation and the Poisson equation. Suppose we can solve that, then essentially we have all the information about the system that we want. We can, for example, we can determine the streaming velocities, the mean streaming velocities of all the stars in a particular position by working out that integral. So we average the velocity of the stars over the distribution function. Or we can determine what's called the velocity dispersion tensor, sigma, by doing this integral here. So we've already determined the mean velocities, and then we've now looked at the differences of stellar velocities relative to the mean velocities at the position. And then we integrate those second-order differences, again over velocity space, and that gives us something that is a quadratic function in the velocities at a position r, or x, in this notation. So that will be the streaming velocity of the stars, and this will be the random velocities of the stars around that streaming velocity. So I think my time is up today, so tomorrow what I'll do is then go on to what's called the so-called stellar hydrodynamic equations, which is the Jeans equations in a stellar system. Then I'm going to look at the tensor theorem a little bit, and then I will start with describing the theory of orbits in galactic potentials.
Thank you.